Good morning, dear cadets. I hope you have enjoyed a good break. Dasara holidays must have enjoyed with your parents and your friends, your brothers, sisters, and all. Welcome back again. We have been discussing about the property of elasticity. If you remember, do you remember? We were discussing about stress versus strain curve for different metals, and we discussed about elasticity property, plasticity property, property of malleability, ductility. Okay, so the graph that we discussed in the previous session, that is stress versus strain graph, will be different for different metals. So based on the graph, based on the proportionality limit, elasticity, elastic limit, ultimate strength, and that's tensile strength and fracture point, based on that extension of the curve or extension of the graph, that particular material is being used for various purposes in the construction designs. Okay, now we are going to discuss another class of materials which we are all aware, which can be stretched to any particular length by applying external force. It can be stretched to any particular length. After removal of the external force, again it regains its original length. For example, rubber band can be stretched to any length. Even for small applied force, it can have a long elongation. The moment you release the external force, it returns back to its initial length. These are also appearing to be elastic, but these materials do not obey Hooke's law. You know Hooke's law, stress versus strain is linear. Stress is directly proportional to strain, is Hooke's law. So for such class of materials like rubber, Hooke's law is not obeyed. Such class of materials are separated and they are called as elastomers. They are called as elastomers. I have given you example of rubber and rubber-like materials. Like another one is tissue of aorta, which is there present in our heart. Tissue of aorta is also just like rubber. It can be also stretched to any length, any particular length. Again, when it is released, it regains its original length. Such class of materials which have a long elongation for applied small amount of stress are called as elastomers. Elastomers are the substances like rubber, tissue of aorta, which can be stressed to cause large strains. For applied stress, they will cause large strains. They are called as elastomers. But when you draw the graph of stress versus strain, it is going to be a curve. Although there is a certain amount of region where you can find out a little bit of linear region, but although they are possessing a large region of elasticity, but Hooke's law is not obeyed. So Hooke's law is not obeyed by these rubber-like materials called as elastomers. Therefore, they are called as elastomers. I think you got the point. So we loosely use the term elastic. Elastic behavior is different, elastomer is different. Okay, although they are showing a little bit of, they are showing a large amount of elasticity, but they do not strictly obey Hooke's law. Such materials are called as elastomers. And the graph you can see sudden rise in the level of strain. Even for small increase in stress, there is a drastic rise, sudden rise in the level of strain. This is what the graphical study represents. Okay. Now next we shall study about moduli of elasticity. Elastic moduli. That's very, very interesting. Now we are going to learn very important constants called as elastic moduli. We know that from Hooke's law, stress is directly proportional to strain. If we take the ratio of stress to the strain, that ratio is called as modulus of elasticity. Based on the type of stress, we are going to have a constant called as modulus of elasticity. So there are three types of stresses as we know and corresponding strains. As a result, there are three types of ratios, and these three types of ratios are clubbed together in general as elastic moduli. So let us first learn about the ratio of tensile stress to the tensile strain. It is called as Young's modulus. The first one is Young's modulus. Young's modulus is denoted by Y. The ratio of Y is defined as the ratio of tensile stress or it is also called as compressive stress. If it is leading to elongation, then we call it as tensile. If it is leading to contraction, then we call it as compressive stress. Tensile stress to the tensile strain, or correspondingly we can define it as the ratio of longitudinal stress to the longitudinal strain. It is denoted by that ratio as Young's modulus. So Young's modulus is measured in terms of Newton per meter square. See, stress is measured in Newton per meter square, and the strain, for that matter, strain doesn't have any dimensions. So the SI unit of modulus, SI unit of any modulus of elasticity is Newton per meter square, or in another unit is also called as Pascal. So this strength, that is Young's modulus, can be obtained within the linear region of the graph. If you remember the linear region of the graph, stress versus strain graph, the linear region, we got the graph of this nature. So from O to A, we get the proportionality limit, and that ratio of stress to the strain within the elastic limit, within the proportionality limit, that ratio gives us the Young's modulus. So if you take the slope of this, the slope of this gives us Young's modulus. That is delta sigma divided by delta E, where E is to represent epsilon, small epsilon represents strain. So within this linear graph, if you take the ratio of tensile stress to the tensile strain or compressive stress to the compressive strain, that gives us Young's modulus. So this Young's modulus of the materials gives us an idea of how elastic is a body. So in the construction designs of the bridges and you see in the buildings, steel rods are being used. The steel material is used along with the concrete. The steel has a very good Young's modulus. The Young's modulus of steel is about 210 to the power of 9 Newton per meter square. Young's modulus of steel. I am giving you an example. Young's modulus of steel is 200 into 10 to the power of 9 Newton per meter square. And that of iron is slightly less. It is also called as wrought iron. 190 into 10 to the power of 9 Newton per meter square. Beyond this elastic limit, the property of plasticity is observed. Therefore, we have to study the material within its elastic limit, wherein it behaves, it possesses the property of elasticity. So this is one constant modulus of elasticity called as Young's modulus. Young's modulus is this ratio. Okay. So like that, different metals are being given here. Aluminium is having just 70 into 10 to the power of 9. Why of aluminium? It's a light metal. 70 into 10 to the power of 9 Newton per meter square. So this, when you compare these values, so aluminium is not being used since its elastic behavior is quite less compared to that of steel and iron. That's how we identify from these examples. Now the next one is regarding change in shape. When the horizontal, tangential stress is applied, when there is a tangential applied force per unit area, it develops a tangential stress. As a result of tangential stress, there is a tangential strain. That's what we call as shear stress and corresponding shear strain. The ratio of this shear stress, the shear strain, is called as the modulus of rigidity. That is what we call as second one, modulus of rigidity. It is the second kind of deformation where we find a change in shape. Modulus of rigidity. So this is defined as ratio of shear stress to the shear strain. Shear stress to the shear strain. Shear stress is expressed in terms of force per unit area, and shear strain is expressed in terms of theta, as we have discussed earlier. So this is the modulus of rigidity. So modulus of rigidity is denoted by G. The notation for this modulus of rigidity is G. Therefore, G is equal to yes. Now we can write as F upon A theta, where we got theta, if you remember, is equal to delta x upon the length L, where L is the length of the cylindrical object, right? So if you substitute delta x upon L, then it becomes Fl upon A into delta x. So this equation of G is helpful for solving the numerical problems. This is also called as shear modulus. Another name for this one is shear modulus. Both are same. So this is regarding change of shape. Right? Third one is when we take an object, the entire object, into a fluid like water. If an object is submerged in liquids like water, then the entire body is under compression. It is under pressure. So there we define another stress. It is called as hydraulic stress, and that hydraulic stress leads to change in volume, and that particular change in volume we call it as hydraulic strain. The ratio of hydraulic stress to the hydraulic strain is called as bulk modulus, where the entire body as a whole is undergoing change in volume. It is called as bulk modulus. So bulk modulus is as a result of change in volume, right? Change in volume, volumetric strain to the volumetric stress to the volumetric strain. This is also we can define. So bulk modulus is denoted by V and is defined as the ratio of hydraulic stress to the hydraulic strain. So bulk modulus is denoted by B. So this bulk modulus B can be also expressed as Hydraulic stress. Hydraulic stress is the normal force applied per unit area. The normal force applied per unit area is also called as pressure, hydraulic pressure. So pressure divided by change in volume per unit volume. But this change in volume per unit volume is actually decrease in volume per unit volume. Therefore, negative sign is taken. Therefore, if you express this, it becomes minus P divided by change in volume per unit volume. So this is how we come to know the bulk modulus. So by noting down the value of bulk modulus for a particular metal, the materials required for submarine, the materials required for construction of ships, and materials required for the containers, vessels which are used inside the water and on surface of the water are being used. So bulk modulus also plays a very important role in designing the materials required for, in designing the structure of the objects which are used in the fluids or which are used for the containers of fluids, as well as which are used as vessels inside the fluids like submarines and so on. So these are the very important modulus called as modulus of elasticity. And if you look at all these, all are having same SI unit, Newton per meter square. Here also change in volume per unit volume, you see it is dimensionless quantity, therefore it is also having same unit, that is Newton per meter square, that is Pascal. Directly you can see it is expressed as pressure per change in volume per unit volume, hydraulic pressure divided by hydraulic strain, right? B equal to minus P upon delta V by V. So all the moduli are having the same SI units, that is Pascal. Okay, so that's how we study the modulus of elasticity. Some of the modulus of elasticity for the examples you can see. The nickel is found to have maximum modulus of elasticity 260. V of nickel is having 260 into 10 to the power of 9 Newton per meter square as modulus of elasticity. Whereas you see the aluminum is having very less, 72 into 10 to the power of 9 Newton per meter square. Copper is having a better value. Copper is having 140. B of copper 140 into 10 to the power of 9 Newton per meter square. And iron, B iron is having about 100. Iron is having about 100 into 10 to the power of 9. 100 into 10 to the power of 9 Newton per meter square. And that of steel, B of steel, bulk modulus of steel is about 160 into 10 to the power of 9 pascals or Newton per meter square. Okay, these B, G and Y, they represent the values of these Y, B, G help us to identify the metals which are having a very good elastic behavior, and based on that the materials are chosen for constructions and designing of the different constructions. Okay, thank you, have a nice day, bye, take care.